Okay, the part 2, we can continue. Yes, the velocity relative to rotating axis. As I told you in previous chapter, we concentrate on the motion with respect to a coordinate system which has translational motion. But sometimes, or in most of the problems, it's better to monitor the motion of the rigid body using a coordinate system which itself is rotating. For example, here in this shape you can see here we are monitoring the motion of point A using the relative coordinate system x lowercase x y, which is a rotating coordinate system, as you can see, and the angular velocity for this coordinate system is theta dot. So sometimes in dynamics, in real problems, we need to use some coordinate system like this lowercase x and y, and also we need another fixed coordinate system which is uppercase x and y. So in this type of problems, we need the relative velocity and uh, acceleration equation with respect to this coordinate system. So we define a new equation for point A and B. In this equation, VA is the absolute velocity of point A. In other words, it means the velocity of point A in the coordinate system which is shown with uppercase X and Y. And VB, this term, is the absolute velocity of point B, which B is the origin of the relative coordinate system, the relative rotating coordinate system, and this VB presents that the velocity of this point B with respect to uppercase X, Y, Z coordinate system. Omega, as I told you, is theta dot here, for example, and it's the angular velocity of the relative coordinate system, which here is shown with lowercase x and y. R is the position vector of point A in the relative coordinate system, which here you can see we show this with RA with respect to B. So this R is the position vector in the relative coordinate system or in the lowercase x and y coordinate system. And finally, V relative, which is the velocity of point A with respect to the relative coordinate system. Okay, so from now, the lowercase x and y coordinate system, which is a rotating relative coordinate system, we call it relative system. Okay, and the uppercase x and y coordinate system is the fixed coordinate system. Okay, So VA and VB are the velocity of point A and B with respect to fixed coordinate system. Omega is the angular velocity of the relative system. R is the position vector of point A in relative system, and finally V relative, which is the velocity of point A in the relative system. Okay, so from this equation we can find the velocity, the absolute velocity of point A, by using the some data from this coordinate, this relative coordinate system. Okay, this is a very important formula for transformation of a time derivative. When you want to extract the transformation of a time derivative, here you can see this is the derivative with respect to time in a fixed coordinate system, which is equal to the derivative of that parameter in relative coordinate system plus omega cross that parameters, and omega is the angular velocity of the relative coordinate system. So this parameter can be any vector. For example, it can be displacement, velocity, acceleration, and any other parameters. So you can substitute here and expand your relation using this relation, and after simplifying the equation you can extract the relative acceleration equation for one particle with respect to a relative coordinate system. So here you can see this is AA, which is the acceleration of point A with respect to the fixed coordinate system, AB, which is the acceleration of point B with respect to the fixed coordinate system, or the absolute quantity. So these two terms are the absolute accelerations. A rel, which is the relative acceleration or the acceleration of point A with respect to the relative coordinate system, and the other parameters which are clear here. Of course, we have omega dot, which is the angular acceleration of the relative coordinate system. The other parameters are introduced in previous slides. R is the position vector of point A in relative coordinate system. Omega is the angular velocity of a relative coordinate system, and the v relative, which is the velocity of point A in the relative coordinate system. So you can substitute here, and again using this equation you can find the absolute acceleration for each point using a relative rotating coordinate system. And here we have one question. What is the term 2 times by omega across v relative? Here, if you look at this equation, this term in fact is the tangential acceleration, and this term is the normal acceleration, and the other terms are similar to the previous part. I mean, when you use the translational relative coordinate system, we had all of these terms. Here we only have one relative acceleration and this term. The relative acceleration is clear because point A is moving with respect to point B, so it can have some acceleration. But what is this term, and why we have this addition term in our acceleration? You can Google it, and maybe you can find some interesting results for this equation. Just to let you know that this term is usually called the Coriolis acceleration, and it's very important when you want to calculate motion of a body which has a significant velocity with this, in comparison with to the Earth's velocity. For example, in a problem when we deal with, for example, the motion of a rocket, which is moving, and its motion is significant in comparison with the motion of the Earth, this term is very important, and it's crucial to consider this term in your calculations. Okay, some examples to understand this formula. Here we have a disk. The disk rotates about a fixed axis through point O with angular velocity of 5 radian per second, and angular acceleration of 3 radian per second square. At the instant represented in the direction shown, the slider A moves in the straight slot here. Determine the absolute velocity and acceleration of A for the same instant when x is equal to 36 millimeter. Dx to dt, or the velocity of this slider, is minus 100 millimeter per second, and the acceleration, or d2x to dt squared, is equal to 150 millimeter per second square. So at this time, according to this given data, we can conclude that the position is in the right hand side of the y-axis, and the velocity is to the left direction, because here we have one negative, so the velocity will be negative. And finally, the acceleration, which is 150, it must be to the right side direction. Okay, so we can use the relative equations with respect to the rotating coordinate system, but first we need to obtain a coordinate system, a relative coordinate system, and a fixed coordinate system. In this problem, we can use this coordinate system. As you can see, we attach this coordinate system at point B, and this coordinate system is rotating by the disk, because this is attached to the disk, and when this disk is rotating, the relative coordinate system is rotating with angular velocity omega and angular acceleration alpha. So now you need only to obtain the parameters in the equation. For the velocity, you can write the velocity of point A is equal to the velocity of point B plus omega cross r plus the relative velocity. Here it's clear that the velocity of A, or VA, is the absolute velocity that we should obtain this. VB is the absolute velocity of point B, and it's clear because point B is a imaginary point which is fixed on the disk, so its velocity is clearly related to this omega, and you can easily obtain this velocity. Omega is the angular velocity of the relative coordinate system. This relative coordinate system is fixed on the disk, so omega is equal to this omega, I mean both of them are the same, and r, which is the position vector of point A in the relative coordinate system, and in this system it's clearly x, I, and the relative velocity is the velocity of the slider A in the relative coordinate system, so it will be equal to this x dot. So you can substitute and calculate the velocity of A. For the acceleration, we have the absolute acceleration of point A, which is equal to the absolute acceleration of point B plus the relative acceleration of point A with respect to the coordinate system, the relative coordinate system, and it's equal to this term, the x double dot. We have omega dot cross r, which omega dot is the angular acceleration of the relative coordinate system, and in this problem is equal to alpha because the relative coordinate system is attached to the disk, so its angular velocity is equal to the angular acceleration of the relative coordinate system is equal to the angular acceleration of the disk, and r, which is the position vector again in the relative coordinate system, and it's equal to x, and again omega is the angular velocity of the relative coordinate system or disk, and finally the relative velocity is again x dot. So we can substitute into these two formula. You can see it's pretty simple. You need only to calculate some vector calculations, and easily you can obtain VA and AA. The velocity of B, as I told you, because point B is a fixed point on the disk, and this is of course an imaginary point here, this point B is fixed on the disk and is just rotating by disk. Because the angular velocity of disk is omega, at this moment, for this instance, the velocity of B is omega cross r, which r is this length 25 millimeter times by omega, and the direction you can easily calculate this, and the direction is clearly in uh, negative direction of x-axis, of course, at this moment. If you want to use the vector form of the equation, you can write the omega in vector form, which in this problem based on the coordinate system xy, omega is equal to omega k, and at this moment the position vector of point B is 25 millimeter in y direction, so it will be 0.025 j. So we will have omega cross j cross r, sorry, omega is k and r is j, so k cross j is I with a negative sign. And finally you can again calculate this value for the velocity of point B. But as I told you, in this simple example, you can easily imagine the direction of velocity, and it's equal to the negative direction of I or x. So it will be minus 0.025 omega I. For the acceleration of point B, again here we have a fixed point on the disk which is rotating with angular velocity omega and angular acceleration alpha. Again, you can use the vector form, which is omega cross r plus alpha cross r, and then you can calculate the vector form. But here again I use the scalar form. We know that this point B, because it has rotating, and if you use for example the polar coordinate system, easily you can write at this moment it will have a normal acceleration and a tangential acceleration. The tangential acceleration is alpha cross r, and at this moment it will be in uh, positive direction of x-axis, and the normal component, which is r omega squared, and at this moment it's in the negative direction of y-axis, so it will be minus 0.025 omega squared. This is the normal component, and the tangential component, which is 0.025 alpha. Okay, so this is the acceleration of point B, and the next step you can substitute and calculate the velocity and acceleration of point A. For the relative velocity and relative acceleration, as I told you, the relative velocity of point A, if you sit here at point B and look at the slider A in the relative coordinate system, you can see a linear motion of the slider. This linear motion has a velocity which is minus 100 millimeter per second, and also it has an acceleration which is 150 millimeter per second square. The position at this time is 36 millimeters, so you can easily write R V relative and A relative. About the omega and omega dot, as I told you, because this relative system is attached to the disk, so it will be equal to the velocity and acceleration of the disk. So next step, you can easily calculate the velocity of the acceleration of point by just some calculation. Here you can see we can easily substitute and calculate the velocity of point A and also the acceleration. You need only some vector calculations, and finally you can easily extract the absolute velocity and acceleration of point A. The next example, here we have two cars. The car B is rounding the curve with a constant speed of 54 km per hour, and car A, which is this car, the red one, car A is approaching car B in the intersection with a constant speed of 72 km per hour. Determine the velocity which car A appears to have to an observer riding in and turning with car B. The XY axes are attached to car B. Here you can see this is the XY axis which is attached to car B. Here you can see this is the attached coordinate system or the relative coordinate system. Is this apparent velocity the negative of the velocity which B appears to have to a non-rotating observer in car A. So first we need to find the relative velocity between point A and B, and the velocity of point B with respect to A, and the velocity of A with respect to B, and compare these two values, and then we can find out that the response for this question. And also the distance separating the two cars at the instant depicted is 40 meters. So we need to write the relative velocity equation, but here if you write the velocity of A with respect to point B, in this case the relative velocity is rotating, because here X and Y is attached on car B and car B is rotating with the angular velocity. We need to calculate this angular velocity, and here because we have the radius of curvature here is 100 meter, we know the velocity of car B, which is 54 kilometer per hour. So easily you can calculate the omega by assuming that this car is rotating about this center of curvature with angular velocity omega. So we can write the equation for the relative velocity. We know that VA is equal to VB, that we know that VB is 54 and VA is 72 kilometer, because we have the absolute value for these two. So these two are known for us. We need to find the omega, and also we have the R, which is 40 meter. We know the position of car A with respect to car B, and then we can calculate the relative velocity in this equation. So we need to convert the velocities from kilometer per hour to meter per second, and then we can find the omega. As I told you, omega is equal to the velocity of B divided by the radius of curvature. You know that if we assume that this car is rotating about this center here, so its velocity is r omega. Here r is 100. We know that the velocity is 72 kilometer per hour. Sorry, 54 kilometer per hour. So you can substitute and find the omega, and then you can substitute here and finally calculate the relative velocity. And also for the relative velocity between point B and A, or the relative velocity of B with respect to A, if you consider the relative coordinate system is attached to the car A, this time it will be a translating coordinate system. So the equation is this term, VB is equal to VA plus V relative, and we don't have omega because this term is 0, because the coordinate system does not have any rotational motion. This time you can find that the V relative is VB minus VA, and VB and VA are clear for us. VB is 54 and VA is 72. The direction of VB at this instance is in Y direction, and the direction of VA is in X direction. So we can substitute in these two equations and find the relative velocity in two different cases. So the relative velocity of car A with respect to car B is equal to this term, and as you can see here we have omega because the attached or the relative coordinate system is rotating. So relative velocity of car A with respect to car B by substituting and simplifying is 20I minus 9J, and the relative velocity of car B this time with respect to car A, this is different, it's equal to VB minus VA. And if you substitute here, you can extract that the relative velocity in this case is minus 15J minus 20I. And what does it mean? It means that if you sit in the car B and look at car A, you will see this velocity of car A. But if you sit in the car A and look at the car B, you will see this velocity of car B. I mean, in the first case, when you are sitting in the car B, you will see that car A is moving with 20 meter per second in X direction and minus 9 meter per second in Y direction. But when you sit in the car A, you will see that the velocity of car B is minus 15 in y direction and minus 20 in x direction. It means that, in the other words, when you are in car A, you can see that this car B is coming to your side with the velocity of 20 meter per second. But when you are sitting in car B, again you will see that car A is coming to you with the same velocity. But the velocity in y direction is totally different. When you are sitting in car A and you are looking at car B, you can see that car B is moving in downward direction with the velocity of 15 meter per second. But when you are sitting in car B and you are looking at car A, you can see that the car A is going down or in moving in downward direction with velocity of 9 meter per second. So you can see that the relative velocity between car A and B when you are sitting in car B or car A will be different. Okay, so this is the answer of the last question. Okay, by this example we can wrap, and there is some suggested problems. You can go through to these problems and let me know if you have any question. Thank you for your attention, and bye.